Hello and welcome to Bio40 Pre-Lecture 8. Today we continue using recombination frequencies to map genes along chromosomes. Let's start by summarizing what we learned last time about two-point crosses. Genes close together on the same chromosome are linked and do not show independent assortment. We can see this when we analyze the progeny of an informative cross with the double heterozygote. The only reason we can see recombinance at all with genes in the same chromosome is due to crossing over between the genes. Given that recombination frequency increases with the distance between genes, we can use these frequencies to roughly say how far apart the genes are. The recombination frequencies between two genes can range from 0 to 50%, and we define a 1% recombination frequency as being one map unit apart. Since recombination frequencies cannot go above 50%, the only way to map genes greater than 50 map units apart is to look at genes in between them. In general, the more genes you look at, the more accurate your maps will be. To find the recombination frequency between two genes, you need a parent heterozygous for both genes, and you need to know if the genes are in coupling or repulsion. Then you need an informative cross. For genes on autosomes, you need to do a test cross, while for X-linked genes, you can just cross the F1 siblings as long as you only look at the male progeny. Here's our sample autosomal two-point cross. We start with true breeding parents to get a dihybrid F1. In this case, the parental alleles are in repulsion. Then we take the females and test cross them with homozygous recessive males. We know the father always contributed recessive B and C alleles, so the phenotypes will always reflect the allele inherited from the mother. And we can count the recombinant and parental classes and calculate the recombination frequency. For X-linked genes, we again cross true breeding parents to get an F1 dihybrid female with a known linkage relationship. We cross these females with the F1 males and look only at the sons. The Y chromosomes don't contribute anything here, so we can tell which offspring inherited parental chromosomes and which recombinant from their mother based on the phenotypes, which again allows us to calculate a recombination frequency. Three-point crosses look more complicated, but work very similarly in practice. Let's look at VG, B, and PR, three genes on the same autosome. We start with true breeding parents with different alleles for each gene, and cross them to get a trihybrid with known linkage relationships. Here, all the genes are in coupling, though you could easily have situations where some pairs of genes are in coupling and others are in repulsion. Just as before, we need to do a test cross and then look at the progeny. Since the father always contributes recessive alleles, we're not even listing them here, instead just showing the chromosome inherited from the mother. You can see that there are 8 different combinations of alleles that we could see, depending on what crossover events occur, which can look a little intimidating. But it's easier if you just look at things pairwise. Let's start with B and PR. In the parental chromosomes, they are in coupling. So let's identify the progeny where B and PR are in repulsion. That's these 4 classes here. So we sum the progeny in these classes, divide by the total, and find that they represent 6.4% of the total offspring, indicating that B and PR are 6.4 map units apart. Next, we can do VG and PR. Again, the parental chromosomes have them in coupling, and these are the 4 classes that have VG and PR in repulsion, so they're the recombinant ones. They represent 515 of the 4,197 progeny, or 12.3%. So these genes are 12.3 map units apart. Finally, we have VG and B. Parentals are in coupling, these 4 groups are in repulsion, they're 17.7% of the offspring, so there are 17.7 map units between VG and B. With the distances of all 3 pairs known, we can deduce a genetic map. VG and B are the farthest apart, and PR must be in between for the numbers to work out. But you'll notice a small problem here. The numbers don't work out exactly. With 12.3 map units between VG and PR, and 6.4 units between PR and B, we expect VG and BP to be 18.7 map units apart. But our calculations say that distance is 17.7 map units. That's close, but why aren't the numbers the same? Let's look at how we calculated the number of crossovers that occurred between VG and B. We identified these 4 groups as recombinant, and did our calculation. But let's take a closer look at what's happening with these groups. Since PR is in between VG and B, no single crossover event can give us the combination of alleles we see in these two groups. These combinations are only possible if there's one crossover between VG and PR, and another between PR and B. Initially, we ignored these progeny because VG and B are still in coupling. But these 22 double crossovers mean there are actually 44 crossovers between VG and B that we did not account for. So if we redo the calculation to include these 44 events, we get a distance of 18.7 map units. The same thing we got from adding the distances between VG and PR and B. So using more genes is preferable because it allows us to detect more recombination events. From a labor standpoint, it also means doing a single cross rather than the 3 it would take to do one pair at a time. You can still analyze the genes pairwise, compare the values to get the gene order, then go with the shorter intervals for the distances because they'll be more accurate. However, there's an easier way to analyze the data from a 3-point cross. This involves determining the gene order first, and then finding the map units between the intervals. So is this going to be one of those times where I explain the hard way to do something in the video, make you answer a question that way in the quiz, and then explain an easier way in class? Really though, there is one more thing I wanted to bring up before ending this lecture. There's an odd discrepancy in our data which can be hard to see at first. The number of double crossovers we observed was actually less than we'd expect if they were independent events. With 12.3 map units between VG and PR, the probability of a crossover between them should be 0.123. And there are 6.4 map units between PR and B, so the probability of a crossover there is 0.064. If we treat these as independent events, we can use a product rule. So the expected probability of both occurring would be 0.0079 or 0.79%. However, we only observed double crossovers in 22 of the 4,197 progeny, which is 0.52%. The reason for this difference is that the occurrence of one crossover can make it less likely that a second event happens nearby. This is called chromosomal interference. The amount of interference will vary from situation to situation because interference is not uniform between chromosomes or even along different stretches of the same chromosome. You can measure the amount of interference in a given cross using a couple quick calculations. You first calculate the coefficient of coincidence by dividing the observed frequency of double crossovers by the expected frequency. You can get the observed and expected values just as we did a couple slides ago. Then interference is simply 1 minus the coefficient of coincidence. So back to our example where the expected double crossover frequency was 0.79% and the observed was 0.52%. We divide observed by expected to get a coefficient of coincidence of 0.66. 1 minus 0.66 is 0.34, our interference value. The higher that value, the greater the extent of interference. When the observed double crossovers equals the expected, the coefficient of coincidence is 1 and interference is 0, no interference. But when interference is 1, there are no double crossovers. A crossover event between one pair of genes completely precludes the possibility of a crossover between the other pair of genes. That does it for Pre-Lecture 8. Next time we go even deeper in our understanding of genes and learn what chromosomes are on the molecular level.